Welcome to the recursion and folds lesson. We'll start by answering why do we need recursion. Then we'll learn how to think recursively and apply that thinking to produce the sum and product functions. Then we will go over a few steps to make it easier to create your own recursive functions and apply those steps to create a bunch of functions. Then we will identify a pattern and extract it, calling it foldr pattern. And from that, we'll learn about foldl, foldl prime, and when to use each one. Let's get started. Why recursion? One of the most basic functionalities necessary in any programming language is repetition. For example, you have a list of objects and you want to do something to all of them one by one. Or you want to do some calculations 5 times with different values. In imperative programming languages, these repetitive tasks are dealt with using iterative loops. For example, in JavaScript, you can have something like this: a for loop and a while loop. In the for loop, you instantiate the I variable with its first value. You also specify the limit up until when the for loop should run and how to mutate the variable. And in the while loop, you first instantiate the variable, set for how long it will run, and mutate the variable. If we try to create something like this in Haskell, we will have a big problem, and that's the I variable. As we covered in lesson 1, Haskell is a purely functional language, but these two code blocks rely on changing I on each iteration. That means they have the side effect of updating a global state as the program progresses. So, in Haskell, we do not have these built-in looping functions. Instead, we have recursion. And how is recursion better than looping, you say? Here are a few reasons. Everything you can do with loops, you can do it using recursion. And on top of that, there are even programs that you can recursively define that cannot be written using for loops. Many, if not most, functions can naturally be defined using recursion. This means that the way you abstractly think about the function and the way you write it using recursion is highly similar. Also, some functions are more clear and more concise if defined using recursion. And finally, another one is that you can use induction to do mathematical reasoning and prove properties of functions defined using recursion. This is more advanced, but incredibly powerful. Okay, so now that you know that you're about to learn a pretty powerful concept, let's dive in. Recursion occurs when a thing is defined in terms of itself. So, a recursive function is one that is defined in terms of itself. That's it. The concept is really simple. The implementation is what gives most of the trouble. So, we're going to start by defining a function using both a for loop in Python and a recursion in Haskell to highlight the difference in the way of thinking about the problem. For example, let's say that we want to calculate the sum of a list of numbers. Both Python and Haskell have the sum function that already does that. But this time, we're going to create it from scratch. In imperative languages, you will write something like this. Here, you are describing step by step what the program should do. We create a function named sum that takes a list. Then, we create the variable called total with an initial value of 0. Then, for each element on the list, we take total add the value of the element, and override the value of total using the assignment operator. This is not equal, this is an assignment operator. So we are overriding the value of total. We are mutating total. And after the loop finishes, the function returns the total value. As you can see, in imperative languages, we use a sequence of statements to determine how to reach a goal, in this case, the sum of the elements in the list. To easily write recursive functions, you have to get rid of that way of thinking and embrace declarative programming, where you declare what things are instead of how to obtain them step by step. Now, let's define the same function, but in Haskell. As always, the first thing we need to do is to write the type signature. So we know it takes a list of numbers, we choose them to be integers, and returns an integer. Now, based on what that function is, one that takes a list of numbers and returns its sum, the next is to look for edge cases. We take a list as an input. What happens if the list is empty, for example? Well, in that case, we know that the sum of an empty list is 0. We can start by defining just that. Now, besides that, there's the case when there are elements inside the list, so we can also add that case. If we think about what the function sum is on the second definition, it is a function that takes a non-empty list of ints and adds them up, which is the same as adding x, the first value of the list, to the result of adding all the ints in the XS, the rest of the values. So we could do something like this. And now we need to find the sum of all the elements in XS. But wait a minute, we already have a function to do just that. It's the same that we are defining right now. So we can just use it and apply it to the rest of the values. And there you go. We implemented our first recursive function. Why? Because we defined sum using itself. Let's see what happens if we use the function. For example, let's calculate the sum of a list that contains all the integers from 0 to 5. Let's see it step by step. When we use the function, we first provide a non-empty list. So we fall in this case. We take the first value, 1, we add it to the recursive call of sum to the rest of the values. So it's 1 plus sum of a list that doesn't contain 1 anymore. And because this is a non-empty list, we do the same. Take the first value and add it to the recursive call of the rest of the list. And we keep going until we hit the base case or the edge case. When sum is applied to an empty list, we return 0. So that's what we have here. And finally, we have an expression that we can easily reduce to 15. And that's how Haskell evaluates our function. Notice that the base case is the one that allows us to stop the recursion and have a result. If we define the recursive function without a base or an edge case, it will crash or run forever. So, in a few words, with loops, you change the context with a mutating accumulator that wraps the steps to determine how to reach the goal. With recursion, you wrap the function with itself, which creates a new context with the desired mutation, in this case, a changed list. And that function, in turn, calls itself again, setting up its own new context, and so on and so forth. Now, even though this was a complete walkthrough on how to create the sum recursive function, the reasoning may be a little bit too specific to apply to other functions. To make it easy for you to create your own recursive functions, we will write a generic step-by-step that you can apply to any case. Let's dive in. I prepared a slightly modified version of the steps created by the one and only Dr. Graham Hutton. renowned researcher, teacher, and board member of the Haskell Foundation. So, these are the real deal. First, as always, write down the type. This will help you define the function later, and you should always define the type first anyway, even if you're not defining a recursive function. Second, enumerate the possible cases you could have based on its input. Start with the standard ones that we will cover in this lesson and change or refine them as needed. Third, between all the previously instantiated cases, identify which are the simplest ones and define them. These often are the base or edge cases. Or think about what you have available to you. Parameters, functions, operators of that specific type, etc. Use those to define the rest of the cases. And finally, reflect on the function. Can the definition be simplified? Can the signature be generalized? Does it do what you intended to do? You don't always have to go through these steps. Once you feel comfortable, you can skip a few or even write the function right off the bat. In general, the base or edge case is usually the identity case, a case that doesn't modify the results, but just stops the recursion. Here we have a few examples. These are two common standard patterns. For recursive functions that take non-negative numbers as input, you usually have a base case of 0 or 1, depending on the operation, and a recursive case of n, any other number that is not 0 or 1. Why 0 or 1? Because those are the identities of many of the operations you will use. For example, 0 is the identity operator for plus, because if you add 0 to something, it's still that something unchanged. 1 for the product operator, and so on and so forth. Another case is for recursive function that takes lists as input. In this case, you usually have a base case of the empty list and the recursive case of the non-empty list. So, taking that into account, if we want to modify this sum function to calculate the product of the elements, and we just change the recursive case like this, we just change plus for the multiplication operator, we will run into the problem that the function will always return 0, because all the elements of the list get multiplied by 0 at the end of the recursion, due to the base case. So, instead, the correct way to define the base case for product is to provide the identity for the product operation, which is 1. And there you go. We have our second recursive function defined. Practice is what gives you the intuition needed to quickly define recursive functions. So, let's define a bunch of functions to get that intuition going. Let's start with the AND function, a function that returns true if and only if all the elements of the lists are true. I added the prime to the names of all the functions that we're going to define because they all already exist in Haskell. After this lesson, you won't need to actually define them in your code. You can just use them. The AND function takes a list of booleans and returns a boolean. Translating that to the type is just this, a list of booleans to a boolean. Now, because it takes a list, we will define the standard case for lists, the empty list and the non-empty list. The base case might be not that obvious. Sure, we have just two values to pick from because it's a boolean. But which one? We will start with the recursive case. Now, let's think about what we have available to us. Because we're dealing with a boolean, we have access to all the boolean operations. And there's one that does exactly what we need, but just for two values. And that's the AND operator. The AND operator takes two values, and if both are true, it returns true. Any other case, it returns false. So, the first element combined using the AND operator with the result of processing the rest of the list, gives us the desired result. So we can do just like this to combine the first value with the result of processing the rest of the list. And now we have to return true if and only if all the elements inside of XS are true, meaning that we need the same function we are defining right now, so we can use it and apply it just to XS. And now the base case is obvious. If we use false, it doesn't matter which list we process, we will always return false, because the AND operator having false to its right, it will always equals false. But if we use true, we won't modify the result, because the result of applying AND true to its right depends on the missing left side. So if there is a single element that isn't true in the list, it will give us false all the way until the end. Else, it will give us true. Another way to figure this out is to figure out that true is the identity for the AND operator. Replacing the base case, we get the final result. And as you can see, if we have a single false, we get false, but if we have all truths, we get true. So it works as expected. In this definition, there's not much we can do about simplification, so let's move on. Now we're going to define the length function, a function that gives you the length of a list. To calculate the length of a list, we have to take a list and return an integer. And because in principle we won't operate on the elements of the list, we can use polymorphic type for the list. Because it takes a list, we will define the standard cases for lists. Looking for easy cases, we can identify that the length of an empty list is of course 0. So we replace that. And now for the recursive case. We can calculate the length of a list if we add 1 for each element of the list, right? And because we have the first element x singled out by pattern matching, we can add 1 for it and recursively calculate the length of the rest of the list, like this. As you can see, because we are not passing down x, this list will be shorter and shorter until it's empty when we add 0. So we will get a bunch of 1s adding together until we get a 0, and that's the length of the list. That one could be our final function. But looking for improvements, we actually see that we don't use x in the body of the recursive functions. So we can ignore it in our pattern matching to obtain our final function. So far, so good. Now let's implement the reverse function, a function that reverses a list. To reverse a list, we have to take a list of elements and return a list of elements. And because in principle, again, we won't operate on the elements of the list, we can use a polymorphic type like this. Because it takes a list, we will define the standard cases for the list. We see that the reverse of the empty list is just the empty list. So that's the easy one. And that's also the base case because it's not recursive. If we take the first element, because it's already singled out by pattern matching, and put it at the end, and we keep doing that until we reach the end of the initial list, we will obtain a reversed list. So we just need to take x, put it at the end, and do the same recursively until we run out of elements, which is our base case. For this, we can use the concatenator operator and recursively call to the left the reverse with the rest of the list, and to the right, because previously was to the left of xs, now we need it to the right, is a list containing just the single element we want to move from the front to the back. We can use this function with any type of list and we get the result that we wanted. Okay, we saw enough easy examples. Now let's do something a little bit more complicated. We will define the drop function. Drop function removes the first n elements from a list. It takes an integer and a list and returns a list. And because, in principle, we won't operate on the elements of the list, we can use a polymorphic type, like this. Okay, this is new. We have two different arguments to take into account now. The way to do this is to present all possible standard pattern combinations. Because we have numbers, we initially take into account the pattern for 0 and any other number. And because we have list, we have to take into account the pattern for empty and non-empty list. So we have 4 different cases for the 4 possible combinations. As you can see, there are more things to take into account, but it isn't necessarily more difficult. Let's think about each case individually. In the first case, if we drop 0 elements from an empty list, it makes sense that the result will be an empty list. In the second case, if we drop 0 elements from a non-empty list, we return the same exact list. And in the third case, if we drop n elements from an empty list, we can return either an error or an empty list. We choose to return an empty list. So replacing those definitions, we get this. We completed 3 of the 4 cases. Now, what about when we want to drop n numbers of elements from a non-empty list? We already have the first elements separated from the list. So if we remove that one, it's one less element to remove. But if we do something like drop n excess, the function will keep dropping elements until the list is empty. Luckily, there's an easy solution. If we recursively call drop with excess, we'll be dropping one element on each recursive call. The first one. So we can subtract 1 from n on each call to keep it sync. That way, if there are more than n elements, we will stop the recursion when we reach n equals 0. So we get this. This way, both parameters are in sync. Okay, we have a working function, but there are a few things to be improved. The first one is that both cases that take an empty list return an empty list. So we can ignore the int in those 2 cases. And also, in the second case, we just pass through the inputs as the result. So there's no need to pattern matching. And finally, we don't use x in the recursive case, so we can ignore it. Doing those changes, we get this. For all the cases when we have an empty list, we return an empty list. When we need to drop 0 elements, we just return the same list we got. And because we don't use n, we can just ignore it. It looks like we arrived to our final drop definition. But did we really? What happens if n is less than 0? Theoretically, it doesn't make any sense. How will you drop -3 elements? But in practice, someone could be crazy enough to try it. In that case, our current function will keep dropping elements one by one until it runs out because it will never get to the case of n equals 0. That could be a way to handle the case. But intuitively, you will think that dropping a negative number of elements would do the same as dropping 0 elements, meaning nothing. So, we have to adjust our definition to accommodate that. And to do it, we can change the case that handles n equals 0 to handle n is less or equal to 0 by binding the number to the variable n, like in this case, but in this case, and using guards to check for the desired property. Like this. I want to remove all this. We don't need it so far. And In this case, this is the only thing that it changed. Instead of pattern matching for 0, with pattern match for any n, and using guards, we check that this n is less or equal than 0. In that case, and only that case, we take the initial list and return it back. In any other case, we fall back to the recursive case. And to prove that it works, here we are dropping -3 elements from the list and we get the same exact list. And of course, you can use the drop function and compose it with other functions and also partially apply it to create incredible useful functions. Now let's talk about the take function. Take takes and returns the first n elements from a list. This function is oddly similar to the drop function. It takes an integer and a list and returns a list. But this time, the returned list contains all the elements from the first one up until n. Because we just saw a similar case, we'll do the first and second steps together. So we have a function that takes an int and a list and returns a list, and we have all the cases for numbers and lists. Same as before, let's think about each case individually. If we take 0 elements from an empty list, it makes sense that the result would be an empty list. If we take 0 elements from a non-empty list, we take nothing, so we return an empty list. If we take n elements from an empty list, like before, we can choose to return an error or an empty list. We choose to return an empty list. Replacing those 3 cases, we get this. Well, that was easy. Now for the recursive case. Like the last time, we also need to reduce n by 1 on each step. But unlike last time, now we want to keep the element on each step. And there's an easy way to do it. We can prepend the element using the cons operator to a new list that will keep getting recursively bigger until we either reach n equals 0 or we run out of elements in the list. Translated to code is this. Here, this part is the same one as drop, but now instead of forgetting about the first number, in this case, we prefix it to the recursive call of take. So we will get a list at the end. Now, we can simplify the expression in 2 different ways. If n equals 0, we don't care about the list. We will return an empty list anyway. And also, if the list is empty, we don't care about the number. We will return an empty list anyway. We can just do that and get this. If the number is 0, we ignore the list and return empty. If the list is empty, we ignore the number and return an empty list. We do have the same problem as we did with drop. Intuitively, taking a negative number of elements should do the same as taking 0 elements. It should not return the whole list like now. Luckily, we already know how to solve this problem. Same as with drop. We pattern match the value of n, and we check in a guard that n is less or equal to 0. And that's it. We have our take function that works as expected. Now let's see how to define recursive functions that takes functions as an argument. Let's start with the map function. Map is a higher order function that applies a function to every element on a list. As always, let's start with the type. We will have a function and a list, and we will return a list. And because we don't really know the function that will be passed as an argument, we will use a polymorphic type variable, like this. The first argument is a function from A to B, and the input list is a list of A's and returns a list of B's. Now let's enumerate the cases. In the case of a function, there's only one case. You get the function. So taking into account the standard cases for lists, we get these two cases. The case for an empty list and the case for a non-empty list. If we don't have elements on the list, we just return the empty list, which will be our base case. And also, we won't be using the function in this case, so we can just ignore it. Now for the recursive case. We have to apply the function f to every element and return the list. So, we could apply f to the first element x and prepend it, like before, to the recursive call of using map applying to xs, like this. And we got our final function. As you can see, we apply f to the first value and prepend to the recursive application of map to f and xs, the list without the first element. As you can see, we can pass the +1 function to add 1 to each element of the list. We can also pass the function to concatenate the exclamation operator to every word of the list. And we can do also more useful stuff, because this is an incredible useful function, and you will use it quite often. Now, let's do one last recursive definition before learning about foldls. Let's define the filter function. Filter filters the elements of a list that don't satisfy a predicate. We use this function quite a lot, so you know how it works. It takes a predicate and a list and returns a list with only the elements that satisfy that predicate. So, translated to the type, we take a predicate, a function that returns a boolean, a list of A's, and a list of A's because we are not changing the values. We are just filtering, and we will get an equal or shorter list as a result. Now, if we enumerate the cases, the first parameter is a function, so there's only one case. And the second is a list, so it can be empty or a non-empty list. Because we don't have elements to be filtered in the first case, we return an empty list. And because we won't be using the predicate, we can ignore it. It is starting to feel easy, right? Now, let's work through the recursive case. In this case, we have two situations. One is that the element does satisfy the predicate, and the other that it doesn't. We could convey this in different ways, if then else expressions, for example. But I prefer using guards, like this. If the predicate P applied to the first element X returns true, we fall in this case, the case when we add the elements to the list that we will return at the end. Otherwise, we don't. And in both cases, we recursively apply filter to the rest of the elements of XS. Translating this to code, we get this. If applying the predicate to X returns true, we fall into this case, we prepend X and recursively apply filter. Otherwise, we recursively apply filter, but we don't prepend X, so it won't be in the final list. As you can see, there's a bunch of examples. We can filter all the elements that are equal to true, all the elements that contain the exclamation, or we can filter all the elements that square are less than 37. And that's it. You can filter away. We created enough recursive functions to start noticing some patterns. Let's talk about that. This is kind of an spoiler, but we're going to extract the foldr pattern. Now, take a look at these previously defined functions. See if you can spot a pattern. We have the sum function, the product function, and the and function. As you can see, there is a pattern that repeats in every function. There is a base case for an empty list that it returns a non-recursive value, And there is a recursive case for a non-empty list that takes the first value of the list and applies a function to combine it with a recursive call that processes the rest of the list. This pattern has a name. It's called primitive recursion. By now, you know the drill. We're going to extract the pattern into its own function. But first, notice that this pattern assumes that the function that combines the value on the recursive case is an operator. To make it more general, let's modify them to use a prefix function before extracting the pattern. For example, the sum function will become this one. The only thing that we did is to change the function to a prefix function so it gets its two arguments to its right. The product function the same, and the AND function the same. And now we are ready to abstract the pattern. We're going to call the abstraction foldr, because we are folding the list from the right. You will see what I mean when we use it. As always, first we start with the type. So we need three arguments. We need a function to combine the elements of the list. So it should take two elements, these two elements, and generate a new one. We need a base value to start from and a list. So we can write something like this. Notice that the elements inside the list can be anything, but not necessarily of the same type as the result. We don't know what the function will do. So we use a type A for elements on the list and a type B for the result. And for that follows that the base value has to be of type B because it's the same type as the return value. And the function has to be of type A to B to B. Okay, now let's extract the pattern. Let's start by presenting the pattern and we'll go from there. Like we always do, we present the two cases. The case when the list is empty and the case when the list is not empty. When we have an empty list, like we said before, we have a base value. And when we have a non-empty list, like we said before, we have a function, this function, that will combine a value and a recursive call. We already have the base value. It's one of the arguments. And the recursive call is just applying the function f to x and recursively call foldr, but with xs instead of the original list. So we can do just that in the definition. For the base value of empty list, we just take the base value and return it. And for the case for a non-empty list, we apply the function to the first value, and as a second parameter, we recursively apply the foldr function with the same function, the same base value, but just xs. Done. We just extracted the primitive recursion pattern. And to demonstrate that it's actually the same, we will pass the parameters needed to create the sum function and work through an example. Let's see. In this case, to create the sum function and apply it to a list from 1 to 4, we can use foldr with the function that combines the value plus the base value of 0 and the list that we want to process. In the first call, because the list is not empty, we fall into this one. We write the function, the plus, the first value, 1, and a recursive call for foldr with the same first two parameters, but a shorter list. Because the list is still not empty, we'll do the same here, because the list is still not empty, etc., up until here. Here the list is empty, so we fall into the first case when we just return the v. and the value, in this case, we passed as 0, so we return 0. And we get this expression. Kind of hard to read, but in this case, we have the function plus applied to 4 and 0. And then we have the function plus applied to 3 and the result of applying the function plus to 4 to 0. And so on and so forth. To simplify it, I will convert it back to an infix function and we get this. As you can see, we start applying the function from the right of the list to the left of the list. We start with the final number and work through the initial number. That's why it's called fold right, because we fold it from the right to the left. And if we simplify the expression, we end up having 10. Now, we can replace it in our previous definitions to get a much clearer and concise code, like this. We partially apply foldr with the function and the base value, so we can get the sum function that takes the list to be reduced. The product function is the same, but we pass the product operator and the initial value of 1, and the AND function the same with the AND operator and the base value true. If, while defining a recursive function, you find out that you are using this pattern, use foldr instead. That way, everyone, including you 2 months later, will instantly understand what the function does without needing to figure out the recursion. Remember that foldr comes already in Haskell. Speaking of which, the length function fits almost perfectly in the pattern. The only difference is that we ignore x and add a constant value instead. If we could just hard code the first parameter of the plus operator, that would be perfect. Well, why don't create a function that does just that and pass that function instead of plus? We just need to take 2 parameters, ignore the first one, and add 1 to the second parameter. We can easily do that with a quick lambda function. Here length is defined almost exactly the same as the sum function, but instead of using the plus operator, we use this lambda function that ignores the first argument and just adds 1 to the second argument. As you can see, works like a charm. And boom, just like that, length perfectly fits the pattern. So we can replace it with foldr. As you can see, there's certain flexibility. For example, we could implement reverse with foldr like this. Here we are using a lambda function that takes the first and the second parameter, flips them, and concatenates them. So it seems like we could use foldr all day long, but it's not all roses. If, for example, we use reverse with 1,000 or 10,000 or even more numbers, the toll of using the concatenator operator grows bigger and bigger. Why? Well, let's see how the concatenator operator is defined in the base library. As you can see in the recursive case, when the concatenator operator has an empty list as its first argument and any list as its second argument, it returns the second list, because the first one is empty. But if the first list is non-empty, it takes the first value and prefixes it to the recursive call of concatenated the rest of the first list and the second list. As you can see in the recursive case, each time we want to add 2 lists, we first need to work through all the elements of the first list, and then we add the second list at the end. So if we have a list 10 times bigger, we have to wait 10 times more for it to complete. meaning that it takes a linear time in the number of elements of the list to finish. What does that mean to us? It means that on reverse recursive call, each time we want to move an element from the front to the back of the list, meaning every time we do a recursive call, we have to walk through the entire list every time. If the list is long enough, you could go for a run while waiting for it to be reversed. But don't worry, I wouldn't leave you hanging like that. There's a neat solution for this. If we could work through the list from left to right instead of from right to left, we could use the cons operator instead of the concatenator operator. And in each recursive call, we will add the element at the very beginning, not walking through the entire list is needed. Enter the foldl function. Foldl does essentially the same as foldr, but traverses the list from left to right. These are both their definitions. As you can see, the difference lies in the recursive case. In foldr case, we apply the function to the first element, and then the second parameter is the recursive call of foldr. But in foldl, the recursive call is at the very beginning with the same function, but with the modified second parameter and modified list. This second parameter is usually called the accumulator because it accumulates the changes. It's a little harder to see because we didn't extract it from a bunch of examples. But to account for that, let's see what happens step by step when we replace foldr with foldl in the sum function. We applied foldl to the plus operator, 0 as the base case, and the list 1 through 4, same as before. In this case, because the list is non-empty, we apply foldl again. The function is the same, but here in the accumulator, we have the result of applying the function to the base value and the first value. And as a third parameter, we have the reduced list. Because the list is still not empty, we do another recursive call of foldl when we, again, the first parameter is the same, the plus function, but the second parameter is the same value as before, but added to the second value. And of course, the list is one element shorter. We keep accumulating the changes in the second parameter and reducing the list in the third parameter, up until we get an empty list. In that case, we stop the recursion and we get this final expression. We add 0 plus 1, and then we add this with 2, and then we add the result of this with 3, and so on and so forth, changing the function to become an infix function like we did before. We get this 0 plus 1, and the result of that plus 2, and the result of that plus 3, and plus 4. And we get the same result. But notice that now we are traversing the list from left to right. And because now we can traverse the list from left to right, we can just use the cons operator to join the values instead of the concatenator operator. Taking that into account, we can do this. Instead of using foldr, we use foldl. And now the function that we pass as an argument does the same. It flips the values, but now we can combine them using the cons operator. And we get the same result. Now we can compare the speed of the two functions by reversing a list, for example, from 1 to 10,000. I will provide these two blocks of code where we use reverse prime that we created using foldr and the concatenator the reverse that we just defined right here with foldl and the cons operator, and I sum the results so you don't get a long list of elements. If you run these two cells separately, you'll see the difference. And also you will see even more difference if you add 1 or 2 zeros to the number at the end of the list. This is an impressive improvement, but it's not the only thing that changes if you use foldl instead of foldr. For example, the operator itself matters. So far, we haven't encountered this because, for example, in the addition operator, if we use either foldr or foldl, we get the exact same result. But for some operators, the order of the operator can give you different results depending on the direction. For example, consider the minus operator. The result is not the same if you go from left to right than if you go from right to left. This is false because if we write the operation explicitly, we'll get for foldl a minus 10 folding from the left to the right. And for foldr, folding from the right to the left, we get 2. So that's another thing to take into account. And lastly, there's one last thing I want to talk about, and that's foldl prime. All the functions we defined so far have the prime at the end because they already existed in Haskell. And we didn't want to get a collision. But with foldl prime, it's also a function that comes with Haskell, and it works a little differently than foldl. In both foldr and foldl cases, we saw that we keep stacking up expressions until the end. And then we reduce them. Actually, Haskell does the job, not us, but you get the point. This means that if you try to fold a big enough list, you will get a stack overflow exception. If we pick any intermediate step in foldr, we see that we can't do much for foldr since we don't have a single operator with both arguments. For example, 1 plus, and we need to reduce these expressions, and for that we need to add 2 plus, and we need to reduce this expression, 3 plus, we need to reduce this, and for this we need to keep doing the recursion. So we'll always need to solve the recursive function first. But if we take a look at the same intermediate step but in foldl, we see that we could totally reduce this whole expression to 6 before continuing with the recursion. And that's what foldl prime does. To be clear, foldl and foldl prime return the same exact result. The difference is that foldl prime reduces the expressions at the intermediate steps. So it's more efficient because it doesn't build a huge chunk. So if we run something like this, please don't do it, you will get a stack overflow exception. But if you use foldl prime, you'll face no issues. Another detail is that foldl prime does not come with the base library in Haskell. So to use it, you have to import data.list module. Don't worry about importing and managing modules. We will go through that in the modules lesson. But know that if you need to use foldl prime, you have to add this line at the very beginning of your file. So this raises a question. When should you use each fold? Usually, the choice is between foldr and foldl prime. Foldl and foldl prime are the same except for the strictness properties. So, if both return a result, foldl prime is the more efficient way to arrive at the result because it doesn't build a huge chunk. However, that's not the whole story. I'm going to give you some rules of thumb from least to most used fold. When should you use foldl? Rarely, almost never. But it could be a good option if the combining function is lazy in its first arguments, because foldl may return a result where foldl prime hits an exception. When to use foldl prime? When the list to which is applied is large, but definitely finite. You do not care about the implicit reversal. For example, your combining function is commutative, like the plus and the product operators, and you seek to improve the performance of your code. Also, when you actually do want to reverse the order of the list, in addition to possibly performing some other actions to the elements. That's because we are taking the advantage of the implicit reverse. And finally, when should you use foldr? When transforming list into list with related elements in the same order, when transforming infinite list into other infinite list, because if the function bust is lazy in its second argument, foldr will lazily generate the results, computing only as much as is required. Also, when folding functions can short-circuit by yielding a result that does not depend on the value of the accumulated parameter. For example, if you're creating a product function that multiplies all the elements in a list, and in the middle of the list there's a 0, you know that from that onwards you will always get a 0. If you keep processing the list, you are wasting time and resources. So you could terminate early when the element is 0. And finally, if you're not sure what to use foldr. It's usually the right choice. Remember that these rules of thumb do not necessarily always apply. And because going through all the whys of these rules could take a whole class, we'll leave it for the curious or for when you happen to need it. I will leave a link with more information at the end of the interactive lesson. And that's it for today. We covered quite a lot of subjects. Make sure to do your homework, and I see you in the next one.